Yeah, it's just, can you track back through the chapter? Yeah. Oh, okay. Oh, wait, Nick, 30 centimeters? Yeah, I think I forgot to put my decimal there. Thank you. All right, so it's like kind of just tracking back through. So the easy ones, this is 1 over f, right? So that's easy. That means 0.5 seconds. Okay, and then omega is what? We went through several things yesterday. What did I say? Yeah. You know what? I'm going to cheat because I want to finish this fast. That and my brain hurts. So simply see if I can do this the fast way, because I would actually like to get to the point where we can do the egg breaker activity. But we'll see. What number was this? 15. Okay. Okay. All right, so yeah, for B, it's just omega is 2 pi f. I remember yesterday when I mentioned that omega, angular velocity, is just the total angle divided by the time. So it's 2 pi over t over the period, and 1 over the period is the frequency, so it's just 2 pi f. That's where they get this. Then C, they asked for, what did they ask for C? Oh, the amplitude. So then they're saying use the total energy conservation, saying the amplitude, the potential energy at the amplitude. Amplitude always means like max amplitude, right? So A is always like the absolute farthest that you pulled it back, or as far as you compressed it and then let it go. We don't know if 5 centimeters is that compression or not. We just know that at 5 centimeters, that's what this is. So what we can say is the original potential energy is equal to the potential energy at 5 centimeters plus the kinetic energy at 5 centimeters. You see, so if I asked you, how do you know that 5 centimeters is not the maximum amplitude, what could you say? They told me that at 5 centimeters, that if the stretch is 5 centimeters, then there's a velocity of negative 30 centimeters per second. If that's true, by looking at that, you should be able to tell me how you know that 5 is not the max amplitude. How do you know that? Yeah, because if 5 was the max amplitude, what should be the velocity?
0.
Does that make sense to you? Right? Because think of like a pendulum. When you get to the maximum displacement away from the equilibrium, what's its velocity? 0, because it stops and goes back the other way. Question? Yeah.
The potential energy, isn't that MV initial? Or is that 0 MV?
Yeah, they're just saying it's this.
But isn't that what you just said, that like its initial velocity is 0?
It's initial. Well, they're saying that at time 0. So yeah, so it's like we're catching this thing in the middle of action. When we started observing, it was already at 5 centimeters, and it already had a velocity of negative 0.3 meters per second. Oh, yeah, sorry. Pandora's playing.
I was like, what the heck is that?
I know, just
No, it's nice. It's nice.
Skate the heck out of me.
what type of song is that?
I don't know. It's like I can't play actual Christmas music because that would be like religious or something. As if any Christmas, what is there, like only like 1 out of every 10 Christmas songs are religious? But anyways.
Yes, Rudolph the Red-Nosed Reindeer.
Exactly.
Yeah.
Frosty the Snowman, Santa Claus. But anyways, so in order to avoid that, I play instrumental music, Christmas music. So in my head, I can sing the song, but then nobody. Yeah.
So, what is
All right. Anyways, yeah. So does this make sense? So what we're doing is we're saying the total energy that it has now has to equal the maximum possible energy at max amplitude. And then you'll notice at this amplitude, there is no kinetic energy. That's what we're saying is velocity would be 0. Okay, at that point. So then it's just a matter of solving out for A at 5.54 centimeters. Questions? All right. Then to calculate the phase constant. So we're looking to see if this thing started at some theta, right? Like instead of whatever starting at 9 or at 0, it started at some theta. How do we do that? Well, we just have to remember what our basic statement was. And our basic statement for the position of an oscillating mass was x equals a cosine omega t plus phi. Do you remember this? Okay. So then if you say at time 0, what happens to omega t? It disappears, right? So then we get a cosine phi. All you have to do is use inverse cosine, boom, and you get 0.455 radians. Does everyone see how that works? So see what we're doing? We're just using the definitions over and over to try to make sure that we're familiar with the terms. All right, then for E, the maximum speed, we already know, that's omega A, right? Omega times the amplitude. Do you remember we did that the other day? Or did that yesterday? And then I think we used this, remember, when we were doing the period of a pendulum? I don't know, one of the two we used it. Yeah, the period of a pendulum, we used this truth. And do we see why this is Vmax? Remember, this is the one where I kept saying, in my head, I was doing cosine? Yeah, that's the one. Because V is the derivative of the position function, right? And x is equal to a cosine omega t plus phi. So then V is negative omega a sine omega t plus phi. And when is that omega a function, when is that maximum? When sine is at pi over 2, right? And we know that when sine, the maximum value that sine can produce is 1. That gives us the omega a. Is this familiar? Do you need me to write that out again, or are you okay? Okay, we talked about it yesterday. So yeah, just multiply that and you get your 69.6. So yeah.
Why is omega 4 pi radians?
Oh, this is what we got up here, the angular frequency. Right, because we were told that the frequency of this thing was 2 hertz. Is that right? Okay. So because we're told that, we know that omega, the definition of omega, is 2 pi over the period, 2 pi over t. Well, 2 pi over t is like 2 pi f. See, and that's where this comes from. 2 pi f is omega. So that 4 pi radians just comes from that. Okay. Everybody cool with maximum speed, E? Then on to acceleration. I mean, where did we get this term for maximum speed? We took the derivative of the position. Well, take the derivative of this, and we got that second one. Remember, we used that term also when we were doing the, it's when we were doing the pendulum one, and I used the acceleration, the second derivative of the position function, and I set it equal to the g sine theta. Then we used that to come up with the period for a pendulum. That's just this term right here. So it's just the second derivative of the position function. And remember, once again, cosine or sine, either one, the maximum value can be what? Just 1, right? Cosine or sine, the maximum value can be 1. So we don't even have to worry about any of that cosine sine junk. Okay, it's whatever it does, whatever maximum it is, it's 1. And then the stuff before that, the coefficient, is this omega squared a. So all we have to do is plug in our omega, which we already know, and then our omega a, which we got there. I don't know why they did it this way. You could also take omega squared and whatever. But
So what did they do for F?
for what?
For maximum acceleration? Like,
Yep. They just took the second derivative of the position function, and then knowing that sine or cosine drops out at 1, like the maximum value can be is 1, there's a 1 here, there's a 1 right here from the sine or the cosine, doesn't matter which. And that just leaves that omega squared. Right? Do you see what I'm saying?
Sort of.
Okay, I feel like people are not clear on that, so let me just revisit it for a moment. Remember that we said x is a cosine, remember we said this, x is a cosine theta, and then we said it's a cosine omega t, and then we said it's a cosine omega t plus phi. Now, take the derivative of this, and you get this, right? Well, I guess technically that's x of t. And then this v of t, right? You get the negative omega a sine omega t plus phi. And this right here is how you get v max. Because you say, what is the max value of this? Well, the max value of sine blah, blah, blah is 1. So the max of this is omega a. And of course, the max wouldn't be the negative, it would be the positive of this. And we know it's a sine function, so it goes plus 1, minus 1, plus 1, minus 1. So then the max value for v is omega a. That's where we got that. Now we take the derivative of this again, and of course derivative of sine is just cosine, so we get negative omega squared a cosine omega t plus phi. So now we see what is the max value of the acceleration. Once again, cosine is going to go from 1 to negative 1. So our max value is going to be positive omega squared a. And that is where we get this.
Oh, so you just use positive omega squared a?
Yep, that's it. That's all you have to do.
And then you just multiply, you could just square the omega. And then
Yeah, they did it weird. I don't know why they did that. Whatever, who cares? Then G, the total energy. Yeah. You could also find the total energy by using 1/2 Ka squared, right? We calculated that. That's fine, whatever. You could also get it from just adding up these two things. It should all be the same value. They just took the Vmax. Hopefully that makes sense to you. Okay. Where does this Vmax occur, by the way? In an oscillating object, a harmonically oscillating object. Where does Vmax occur?
when the sum of the forces is equal to 0.
Okay, and that would be the easiest way to say that. Of course, you could say where the sum of the forces is 0, or you could say at the equilibrium point. At the equilibrium position, that's where the max velocity occurs. And then finally, the position at that time. So if we expand this a bit, it looks like you just take all the things that we already know plus the position function. I'm sorry, not plus. Take all the things that we know and plug them into the position function. If I jump back over here, is this not, sorry, right here, is this not the position function? Do we know A? Yes. Do we know omega? Yes. Do we know time? Yes. Do we know phi? Just plug everything in and get your answer.
Oh, so you're just using all the stuff to do for
Yeah, so they're just saying use the position function. Yeah.
So all three of those are position functions?
No, be careful. Oh, even this. Yes, you're right. Yes, yes. These are all three the same statement. It's just they're made more specific. Because this one, actually, technically I shouldn't put that. Because x of t is here. Because this is the position function. This is position as a function of angle, as a function of theta. This one, finally, because it has a t in it, is position as a function of time. And then this one is position as a function of time with a possible initial angle. Questions? Yeah.
For amplitude A, is it the displacement from the equilibrium, or is it from
Yeah, it's from equilibrium. From equilibrium. So it's kind of like, you know how like we talked about x right here? A is max x. That's why here, if cosine, what's the max value of cosine? 1, at maximum, A is x.
So then if the equilibrium point is a given distance x from 0, then the max amp would be A plus x.
Sure. Oh, you mean like for like a suspended spring? Yeah. Yeah.
Can you go back to part C?
Sure. C was the amplitude.
That's what
Yes.
B equals omega square root a squared minus x squared.
You said V equals
Omega square root of a squared minus x squared.
a squared minus x squared.
It's all right.
V is omega. Oh, so you use like rotational equations? Why can you not use V?
I still got 5.54.
So you get the right answer?
Yeah.
Well, I mean, I guess since it's harmonic motion does, follow the same pattern as circular motion, which is why we get away with this sine or whatever, cosines and sines. So, interesting. I wouldn't have thought to use that. That's clever.
Wait, so you can use rotational equations to figure out the acceleration?
Yeah, like how we turned x equals blah, blah, blah. We turned all of that into theta and omega and alpha.
Uh-huh.
Yeah, I think he's saying that's what he did. So wait, say your equation again?
V equals omega square root of a squared minus x squared.
A squared. Oh, that's just from the book somewhere, right?
Yeah, somewhere right
Yeah, okay. Oh, okay, so that's like some sort of transitive form of the final equation, which says, like, the period is 2 pi squared of m over k. In the derivation of that, somewhere there was a form where he saw an equation in the chapter that had all the variables he needed, and he just used that and it worked. And that the reason it worked is because that's ultimately what he would have used to come up with the description of the period for a spring mass oscillation. So that's fine. But this is just a general case operator. Okay, and yes?
I'm just confused about, like,
Shh, please.
if it's just a spring oscillating like on a horizontal axis,
Uh-huh.
like, where's the angle in that? Or where's your reference point to pick for that angle?
Okay, maybe if you think about it like this, if you're on a merry-go-round, does it make sense to you that every period you're exactly where you started? Okay, but there's but time has gone, and if you think of not just time, but you've traveled like an angle, right? So now if you put yourself on a spring that's oscillating, do you see it's the same idea?
But if you're just oscillating, I don't see the angle in that.
Well, I mean, do you see the similarity between the two cases?
Yeah, I see how you're traveling too.
Okay, so because of that, that's the link. The link is not that there is a direct relationship, it's that a spring mass combo or a pendulum are objects that are called harmonic oscillators. They mimic rotational motion. So it's simply the case that somebody was farting around with this stuff and looked at all the numbers and said, holy crap, they match. And why do we even need to do that? Because now we have a mathematical model to describe the behavior of springs and pendula, and not just that, but any object that is harmonically oscillating. So for example, like the tip of an airplane's wing at high speed, right? Because of the nature of the materials, it's going to oscillate harmonically. We can create mathematical models for that. So it's not the case that there is actually some direct link. It's that they just behave the same way, and therefore we use that math model. Other questions? Yeah.
For the energy conservation, is it 1/2 kx squared for a spring?
Yes. Isn't this a spring? I thought it was a spring on a mass.
Okay, so that's like 1/2 kx squared would be the energy of our oscillating object.
1/2 Ka squared would be the maximum potential energy stored in the spring. Yeah, you see, because the Kx squared, that's potential energy. Does that make sense?
Wait, kx squared is potential energy?
Yeah, 1/2 Kx squared is potential energy. Potential energy in a spring. The elastic potential energy.
I'm trying to remember. I'll look it up again.
Okay, other questions? Yeah. Please.
I'm solving for amplitude in a different way, but I'm not sure if this method is valid.
Okay, what'd you do?
First, I took the position function xt,
Uh-huh.
and then I took the initial initial time t equals 1.
Okay.
And then I wrote 0.05 equals a cosine phi.
Okay.
0.05 because I converted to meters.
Right, because you just used the initial position, yeah.
And then I took velocity function vxt, and then the initial velocity negative 0.3 meters per second. After solving for omega, I plugged omega in, so then negative 0.3 equals negative 4a sine phi.
Mm-hmm.
And then I isolated a in both those equations, set them equal to each other.
Yeah, that's fine. That's kind of like, we had this experience. I mean, now when you hear that, I see people, after about the third thing that he said, people's eyes glazed over. And they're like, okay, whatever. It's not because it's basically what he did, and we saw this in chapter 2, right? There's multiple ways to get to the answer. Like you can go through this equation, or because these equations are built off of each other, you can take these two equations, do these things independently, put them together, and get the answer. So it's simply that concept over again. So yeah, that's fine. That works. Okay. All right. Good. So I think we're done with that one. And that movie is like